So today I'm going to talk about agent-based models of collective animal movement. So one of my goals over the next few days, next few classes will be to cover more agent-based models. Okay. So to that end, I have chosen collective movement. Okay. So basically, up to now in the class, we have had agent-based model of random walk, right? And we studied various properties of it, various analytical properties, how to apply them, and so on. And then another model we also looked at, agent based. You can call it agent based model again of how population you know gives rise to birth and death and grows or changes over time on a spatial lattice. Right? Again, we were really thinking of each individual as an organism or an agent there. Okay, that was another model we considered. And then I had shown you one model of binary choice, right? And then you yourself constructed predator prey models. They're all sort of agent based models. So while the models like population dynamics have agents that give rise to birth and death, so basically they are over a longer time scale. Movement models are typically, within a lifespan, right? So there will be no birth or death in these type of models. Okay, so the motivation for studying collective movement comes from a phenomenon that we observe in nature, where you see that a large number of organisms, they come together, they group, and they move in various types of, highly coordinated ways, as if they have a single mind. Okay, and there are many functions of being in groups. In this example, you sort of clearly see that there may be an evidence, there may be something to do with the to evade from predatory attacks. Okay, so here I know in this course, I don't think I'm going to talk about the functional aspects, more on the proximate or the mechanistic aspects. Okay. So there were many models that were developed to understand these kind of behaviors, and surprisingly, these models actually typically came from non-biology literature than in the biology literature itself. And in fact, the earlier models were in 80s. Computational models were built in 80s by computer scientists and so on, and various modifications of those were also began to be used in animation movies. For example, you may know the famous Stampede, that you saw in the Lion King movie. Okay, so that actually used various principles of collective motion, although they did incorporate much more complex features than the one that you will see in the class today. And if you go back in the literature, I think there were some attempts at various ways to think of these kind of agent-based models. Even in back in 50s and 60s, but not very prominently followed up later on, perhaps due to lack of computational power. Okay. But this paper, what's called Vijay Model of Collective Motion, published in Physical Regulators in 1995, really kicked off the whole field of collective motion. Okay, so what does this model do? So this paper, I'm going to use a bunch of text from the paper to sort of say what the paper authors wanted to say. They say that the paper is motivated by physics of non-equilibrium systems. We introduce a model with a novel type of dynamics in order to investigate clustering, transport, and phase transition in non-equilibrium systems. Yeah.
Yeah, I think we are not seeing this presentation. We are just seeing the first slide.
Oh gosh. Oh gosh, it's a bit of a shame because I showed you a video and so on and so forth. Okay. I don't know what happened. So I'll just unshare and share again.
So we're just seeing the PowerPoint window on the first slide.
This one?
Yeah.
What about now? What do you see now?
Now I can see.
What about now?
We are on the PowerPoint window, not the presentation.
Now?
Just the window, yeah.
Nothing has changed?
No, just the first slide.
Oh gosh, okay. Then I think what I will do is something very rudimentary. I think this happened to me sometime last week somewhere when I was giving a talk. It's very strange. I don't know why this happened. So I'll just zoom in as much as possible. Okay. So this was my first slide. I think this is this okay now? Reasonable coverage of the slide.
Yeah.
Is this better now? Okay. And this was the second slide where I showed a video. So I said in this video, so maybe you didn't, we're expecting the video will come, I suppose, right? Okay. And then, okay. So then I was in the third slide. Okay, this was the slide I was on. When you told me you are not seeing my slides. Okay, this is so basically this paper was motivated by physics of non-equilibrium systems. Not as much, to explain truly the collective behavior in animal groups, but that was indeed the motivation. Okay, so we introduce a model with a novel type of dynamics in order to investigate clustering, transport, and phase transition in non-equilibrium systems. And in this model, what they do is they assume just a single rule, which is that at each time step, a given particle driven with a constant absolute velocity assumes average direction of motion of particle in its neighborhood. Okay, so this assumes a very simple, rule. Although the sentence looks long, what this is basically saying is that each individual is moving at constant speed. Okay, and it just follows the direction of the neighbors. That's what it means. Okay, so the paper goes on to say that this model is interesting because of possible biological applications. In addition to such trivial examples such as schools of fish, flocks of birds, etc., our model can be applied to the less known phenomena during bacterial colony growth. So in fact, there's actually a sort of an accompanying paper that came around the same time where they really make an attempt to look at bacterial colony growth. That was again one of the very first papers in the field of self-organization and collective behavior. And of course, it also then provides many other physics motivations like the transport and clustering phenomena. Okay, so let's see how this builds the agent-based model. How this paper builds the agent-based model. This model assumes that the space is continuous with the dimension of L units by L unit. Okay, it implements something condition in this class before. I don't remember. So basically, what this basically means is that if we have a space, imagine if this slide was a space. Okay, so if you now, I'm taking my cursor out of the right side of the slide. Okay, now imagine a scenario by taking outside the right side of my slide. Imagine I came back from the left side like this. Okay, so imagine I go like this, like this, like this, like this, and a particle that leaves the window comes basically back from the left side. Okay, so likewise, if the particle leaves the space up, now here, okay, where does it come? It comes from below. Okay, so if that's called periodic boundary condition, meaning that this edge here is wrapped to the other edge. So in fact, if you wrap this in 2 dimensions, if you do it in 1 dimension, you have a ring. If you have between 2 dimensions, you have a torus. Okay, so this model assumes periodic boundary conditions. Okay, and so if you are to ever do a simulation of this, you need to take care of the distances very carefully. Okay, now it assumes there are n particles in this L by L size who all have identical properties. Okay, and then it starts with this initial condition, which is that there are n particles which are randomly placed in space. Let's say they have some coordinate xi of t and maybe yi of t, At t is equal to 0, their positions are randomly given, and they also are given a random orientation. Okay? If vi is the orientation of the velocity, you say that it's any of the 360 degrees randomly chosen for each individual, uniformly randomly chosen. So that's the initial condition. Now they are placed randomly in terms of coordinates, they are oriented randomly. Now what do these agents do? They follow this very simple rule. This is from your high school physics. X, the position at a new time step is the position at the previous time step plus the velocity times delta t. Okay. So in each delta t time unit, which is chosen as 1 unit, by the way, okay, it just moves in the direction that it's heading. Okay. Each particle does it. Okay. Now here is the thing. What is this VI? VI itself depends on the theta, right? VI, the speed is constant, some speed is given, but the VI also has a theta. What is the theta? Okay, so theta is basically given by this. So theta at the new time step is given by theta, angular bracket R. What this basically means is that if I measure the heading, the theta of all other neighbors within a radius R around me, and then if I take the average of all of their velocities, all of their orientations, and that will give me a new direction, and from that find the new theta. That's what this basically is telling. You basically take the average of the orientations of your neighbors within a distance R, within a radius R of the particle I, and then you move with the direction, except that there's a delta theta here. Delta theta represents stochasticity. So this model assumes that this delta theta is a random number chosen uniformly between minus eta by 2 to plus eta by 2. Where there is some number. Okay, basically if eta was pi, it's minus pi by 2 to plus pi by 2. Okay. So there is some element of randomness when every agent moves, although it's following the neighbors. Okay, and then every neighbor moves, updates these positions and the directions synchronously. Okay, so these are the rules of how the agents move in this model. So any questions before I go forward? Do you all are the rules of model clear? Oh, can you hear me? Okay, so now moving forward, can you hear me? Can you please in my earphone? Can you please confirm me if you can hear me?
Yes, sir. You're
Yes,
audible.
sir. Thank you. So let us see what this agent-based model produces. So you're seeing 4 panels here. You can see that in A, B, C, and D, they all produce different patterns. Now I have sort of forgotten slightly what the exact parameters the paper had chosen for these 4. But what you can see is the following. Okay, in A and C, if I am right, so I think in all the A, B, C, D, the number of agents are same. The N with the particle that we mentioned, they're all same. But what is in A and C, what you have, if I'm right, is that the stochasticity is higher, whereas in B and D, the stochasticity is lower. And in fact, in D, the stochasticity, the eta parameter is lowest. So basically what this shows is that as the randomness when individuals are copying the average of the neighborhood is reduced, you see sort of a what physics would call a phase transition from a disordered state in A, where the agents are all moving in random directions. They're all forming some small clusters, but they are moving in random direction. But they all begin to move in the same direction. The entire population is now moving in the same direction, and in the specific case, they're all moving towards the upward y-axis. Okay. However, when the noise is low and when the number of individuals are sufficiently high, what you see is that they form local clusters, even though all of the local clusters may all be moving on their own, in their own direction. But in D, when the density is high, when the noise is low, what you find is that everybody in the population moves in the same direction. Okay. So basically, this happens by two means. I don't know if I have the slides to show that very clearly. Uh, in this agent-based model of collective behavior, you can achieve this ordered motion by two means: either reduce noise substantially, or you increase the density substantially. So as a function of density, increasing density causes agents to move from disordered to ordered collective motion, or reducing noise again has the same effect. Okay, so now what I showed you was just a visual representation. What you can do is you can quantify the order. Okay, this is called the Wycheck order parameter. What you're basically doing is you take the velocity vector of each individual in each agent, you add them all up, and then you take the modulus of this addition. Okay, if everyone was moving in the same direction, if all n agents were moving in the same direction, the summation, this modulus of the summation is equal to how much?
1.
Just the modulus of this term.
Or V.
But the n particles.
NV.
Exactly. Where V is the speed. If V is the speed, this summation with the modulus will be equal to n times V, because everyone is moving in the same direction. The vectors just add up, right? So basically, what this means is that VA will be equal to 1 when everyone moves in the same direction. So that the picture D, if you compute this Wycheck order parameter, it will have a value of 1. What do you think will be the value for A? Something like A or B, A or C?
0.
Yeah, so we expect that to be equal to 0. They're pretty much moving, on their own randomly. Okay, you can also have a 0 order even when you see that there are local clusters of order. Okay, remember that. Okay, now this is one model that is able to capture some basic features of how animals move collectively. And this is extremely simple model. It had only a single rule, right? The only rule was that every individual moves in the average direction of the neighbors with some stochasticity. There was another model published in 2002 that basically develops and incorporates much more realistic features of what happens in animal aggregates. Let's see what it does. So it has 3 behavioral rules, not just one. So what you are seeing here is sort of a pictorial representation of an individual who is represented by an arrow at the center, and 3 zones. The first zone is called the ZOR, or the zone of repulsion. What does it mean? What this basically means that if there is any individual who is so close, who is within the zone of repulsion, then you basically repel that individual. So that is given by this expression. If Rij is the position vector between the focal individual and the individual within the zone of repulsion, you basically repel in the average direction of all of those individuals. Okay, that's the collision avoidance. That's the first behavioral rule. Now, the second behavioral rule that comes from this second annular region represented as ZOO, zoo. What is it? It's a zone of orientation. Okay, so what happens there? What happens there is the following: if Vj is the velocity vector of the individual in this zone, you consider all such individuals in this zone. Let NO represent the number of individuals in this zone of orientation. You basically move in the average direction of all the individuals, but only within this zoo. Okay, this is something basically same as what Wycheck was doing. The difference is that in Wycheck's model, the ZOR was basically equal to 0. There was no repulsion zone in the Vichek model. Okay, that's the second behavioral rule, that of orientation. The first one was avoidance, collision avoidance. And then this model also incorporates a third behavioral rule. Sorry, this should be attraction. Attraction. This is ZOA, zone of attraction. So what basically this means is, if there are individuals who are beyond ZOO and but are less than some maximum radius ZOA in this third annular ring, if there are any individuals, the focal individual will be attracted towards those individuals. Now that's basically given by this expression. Now, of course, there will be individuals here. There will, for any focal individual, there will be individuals here. There will be some individuals here. There will be some individuals there. So the way this model works is that if there is collision happening, that's always given a priority, and only collision rule is implemented. If there are no individuals within this zone of repulsion, but if there are individuals in both of them, you just consider an average of the effect of attraction and that of the orientation, and then you move in the direction of the average along with some stochasticity. Okay, so this incorporates a few other features. It incorporates stochasticity as in Vichek's model. So once the zone of orientation, attraction or repulsion, if they tell you what direction to move, you move with some stochasticity in that direction. However, it also incorporates one additional rule, two additional rules actually. One of it is that I don't instantaneously move towards a direction. I have an inertia. Individuals have inertia, therefore you move towards that with some rate. And it also incorporates field of perception. So in Vichek's model, individuals could see everybody around them within that radius r. In this model, the assumption is that one can see only some angle around the direction it's facing. Okay, for example, for many organisms like fish and insects, this angle can be actually as large as 270 degrees or even sometimes a bit larger than that. Whereas for humans, it's more like closer to 150 degrees or so. We can't really see beyond 180 degrees almost surely. Okay, so it incorporates a zone of perception which can be modified depending on the organism that one is studying. So it has, as you can see, clearly many more rules, right? It had this turning angle restriction or behavioral inertia. It has field of perception. It had 3 behavioral rules: collision, orientation, and attraction. Okay, there are several more rules compared to the Vichek model. And it also produces a bunch of collective patterns. So what you are seeing on the left side is just an aggregate, more like a swarm, like a mosquito swarm, because in this picture, the attraction parameter is quite dominant in this panel A. But if you look at panel C, you can see that they're all moving in the same direction. They have all grouped and they're also moving in the same direction. And that's because the orientation parameter is very strong in this, simulation picture. On the other hand, in B, when there is some interesting sort of, balance between attraction and orientation, what you see is that the entire group begins to move like in a fashion of torus. They're all basically going in circles. Okay, and that's an interesting pattern that you see here. But this happens when there is typically a large degree of attraction followed by a small degree of orientation in terms of the zonal sizes I mentioned in the model. Okay, so in fact, you do find these kind of patterns in nature. I don't know if I have the video that works now. No, I don't have. Okay. So this is an example of to this torus movement in real organisms. Okay. So but while there is one interesting lesson from here, we began from Vichek model, which had really one behavioral rule, and if we now look at cousin model, it had 2 additional behavioral rules. It had 2 additional constraints on the motion in terms of the field of perception as well as the other one being behavioral inertia, right? Behavioral inertia is pretty much another rule, so it had more rules. So of course, therefore, we also found more realistic patterns
For example, I don't think you would find this torus pattern in the example of check model at all. Okay, so by adding more features, we found even more realistic patterns. So the question one can ask is a useful thing to think about in the context of any biological modeling is, where do you really stop adding more and more features? Okay, that's something I want you to think. Okay, so any questions before I go forward? So I presented two models of collective motion, two agent-based models. One was a very simple model. The second one was slightly more, realistic and had more details. Okay, no questions. I will go forward. I will share another presentation now. One second, give me like 2 minutes, please. How is that? Okay. Can you see this?
Yes, it's visible.
Okay. Okay. So now I'm going to talk about what we call as emergent patterns or also self-organized behavior in a bit more detail, using this example of collective movement again. Okay. Okay. So just a bit of recap from the previous set of slides. So basically, what the basic couple of things we have learned from that, you can actually reproduce certain macroscopic patterns of sort of real biological systems from very relatively simple rules of interactions among organisms. So even what I called as a complex model, the second model, the cousin model, right? Even that wasn't like like too complex like what the real organism does anyway, right? It still had fairly simple behavioral rules, and what we found is an emergent pattern, which I'm going to explain a bit more detail. Emergent patterns, by emergent patterns, what we usually mean is that these are the patterns which are not encoded in local rules, but they emerge as a consequence of large number of interactions that are happening at smaller scales. Okay, let us explain this. Let me try to explain this a bit more. Okay, so here the example of torus pattern, which came towards the end of the previous slides, right? So in the equations of orientation, in the equations of attraction or even the repulsion, there is nothing that says go in the rules that say that individuals must go in circles, right? Yet we found that the entire group began moving in a torus fashion. So when equations do not explicitly have a rule, but you still find that rule sort of suddenly appearing when a large number of agents interact, we can call that an emergent pattern. But this is very vague. This can be sometimes wrong. One is careful about how we interpret emergent pattern. Okay, so one way physicists think about emergent patterns is via the notion of symmetry. So what do we mean by symmetry? Now consider, unfortunately I have given the answer here. Okay, this is because animations are not working. Unfortunately I have the answer here. Let's just, I hope I hope this will, do you see the next point now? No.
No.
Okay. Okay, then I'll just stick to the slides. Okay. So now consider this, a bunch of random walkers, okay, who are moving randomly in space, or a highly polarized population synchronously moving in one direction. So if you were to think of the panel of collective movement I showed, the one part of the panel had everybody moving in the same direction, and the other part had things were just moving randomly, right? At least There was no movement there, there was no animation, but it appeared like they were oriented randomly. Which of the two has more symmetry? I somehow think I had asked this question in this class sometime, one of the early classes. So the answer to this is actually that of random walkers. Okay. See, the basic reason is as follows. When random walkers are moving in all directions, at the population level, every direction is equivalent. There is nothing about there's nothing special about any direction. On the other hand, if you look at a highly polarized population which are moving synchronously in one direction, they have chosen a direction, and that is the preferred direction of the entire population. Okay. In that sense, this highly polarized group has actually less symmetry in terms of directionality than compared to a bunch of random walkers who even don't interact with one another. Okay. So one can use this idea of symmetry to sort of say what is an emergent pattern. Okay. So for example, so basically this, random walkers have more symmetry. Now we introduce interactions among random walkers. Interactions like, align with your local neighbors. Okay. See, aligning with local neighbors has a rule, right? It's an alignment rule, but there is nothing about that rule that says you have to align in the direction of y-axis, right? There's nothing about that says you have to move in the direction of x-axis. So it's just a local alignment rule. But if everybody now starts following this local alignment rule at the population level, they may all choose to go in one direction, and in the example I had shown, it was in the y direction, positive y direction. Okay. So so what that means is that the population as a whole has broken one symmetry that was present before the interactions were introduced. Okay. And whenever you see a broken symmetry, one can think that some sort of a pattern has emerged now in the system. Okay. So again, applying to the example of polarized state, you can apply it to the torus state as well. Equations do not suggest which direction to take. Equations do not suggest that they must go in circles. They treat all directions and all rotations symmetrically or equally, right? In an equally fashion. However, the entire system, because of these repeated interactions, picks one direction in the case of polarization. They pick one direction, one angular direction in the case of torus movement. And in that sense, that symmetry is broken in this collective system. Okay. And typically this broken symmetry is also associated with phase transitions in physics. And one can see that this broken symmetry is sort of equivalent to emergent pattern, because there was nothing about the equations that had this broken symmetry, but they sort of emerge from the interaction rules. There's actually one more example that I can give you from this paper, Cousin et al. 2002, which is, in the context of behavioral interaction. Okay. Now this doesn't fall into a classic, broken symmetry kind of example, but, but I think it is still can be thought of as an emergent property. So here, think of biologically realistic behavior, like, over time, organisms change their behavior, right? For example, their nutritional state might change, their motivational state might change. Consequently, the interactions between them may also change over time. Okay, so let's make a toy example. Let's assume that the individuals change the zone of orientation as a function of time. Okay, and then let's assume a very specific thing, which is that all individuals in the group increase R0, which is the zone of orientation, slowly over a period of time, and then they decrease. For example, something like this is possible. Imagine a group of fish. When the group of fish have low light, okay, they cannot see, therefore they don't interact, therefore they don't align with each other. Okay, so as the lighting conditions increase, for example, during that early morning time, their R0 could potentially increase, right? And then eventually, when the lighting conditions go down, their R0 might reduce. Okay, this is one way this could actually happen. Social interactions change over time. So now, if you now plot the polarization of the group as a function of R0, what do we find? We find something very interesting. We find this. We find this is a figure from Cousin's paper. As R0 is small, but is increasing, you don't see much of the y-axis here is polarization, by the way. It doesn't really change much. Okay, it stays roughly small for a range from 1 to 2.5, and then suddenly it begins to increase. It shows some non-linearities. The entire group polarization rapidly increases, and again it saturates to close to 1. So now, as I told you, the R0 can reduce when the lighting conditions go down. What do you expect under normal circumstances? You would just think that the group polarization will follow this pattern, right? Actually, it doesn't happen. What happens very interestingly is the group polarization actually goes along this direction. It doesn't reduce at all. So once a group is already in a polarized state, even if you reduce the R0, the group continues in a highly polarized state until it undergoes another sharp nonlinear transition. Okay, so what this basically means is that there are two possible states that are that can happen in terms of collective motion: a low polarized state and a high polarized state. And which state do you reach actually depends on the initial condition. Okay, and this is similar to the idea of multiple stable states we said in the context of population dynamics. Okay, and those kind of things can also happen in behavioral states of animal groups. There is what we call hysteresis. There is a history-dependent collective state. Okay, so this is also an example of emergent property. This is something, again, individuals cannot experience on their own. What the individuals are changing is just R0 as a function of time. However, collectively you find hysteresis, although individuals do not have hysteresis behavior. Any questions on this?
Sir, this type of hysteresis is easier to understand than what happens in the case of harvesting, right?
Yeah, this is intuitively a bit easier to understand. You're right. Yeah, a group, the entire group is already in a polarized state, and so therefore, if you reduce R0, right, it's sort of conceivable that they continue in the same direction, although because they are now set to move in the same direction, right? So yeah, you're right.
Yes, sir.
Yeah. Yeah, the other one is going to requires a lot more because there is a birth death process and so on, so it becomes a bit harder to understand. Any other question? That's an interesting observation. Okay, so let's go forward. So now coming back to the biological aspects of it. Okay, now all of these patterns do not require heterogeneity among individual behaviors, right? For example, there's no need for a leader to coordinate and guide the motion of individuals to move in flocks. So now if you were to go to any common person, probably the first question they will ask is, do they have a leader, right? Do flocks have a leader? Do groups of organisms have a leader? And in fact, even scientists think this is a very valid question. However, what these agent-based models show is that you don't need any sort of leadership to sort of explain the pattern of collectively synchronized movement. Okay, so these are basically sometimes also called self-organized patterns because they entirely arise from local interactions that lead to macroscopic self-organized patterns. Okay. Now, however, just because this is true in models do not mean that in real world there are no leaders, right? In fact, it is still a valid question to ask, does it mean that in real animal groups there are no leaders, or is it that we just don't need leaders to achieve these groups, okay, achieve these kind of patterns? Okay, so to really address this question using real animal groups is actually is a non-trivial task. Imagine that I showed you a video of fish moving. How can you tell there are leaders in this or not? How would you go about establishing there is a hierarchy or not in the movement behavior of animals? So of course, if there are some drastic differences between behaviors, maybe yes, you can, but often you don't find such drastic differences. For example, if there was a big individual who was guiding the motion, then you can reduce leadership, or an influential individual. But if there isn't something like that, it becomes a very difficult thing to do so. So is there a way to deduce if there are leaders in groups if we had lots of very, very good data? Okay, let's ask this question. So this can be done by quantifying relationships between individual movements. Okay, so let's ask a very simple question. Okay, imagine a very simple scenario. Scenario one, there are two randomly moving individuals. Another one, there are two interacting individuals. How would you go about quantifying differences in the movement between them? So I was hoping that I will ask you this question and elicit a response, but because my slides and animations are not working for reasons that I don't know, you know the answer now by looking at the correlation. Why so? Can you explain to me why? What do you think will be different between two randomly moving individuals and interacting individuals in terms of correlation in their movement?
There would be more correlation between interacting individuals.
Yeah, absolutely. What kind of quantity will you measure for interactions? Huh?
Direction.
Exactly, right. So if you look at direction of two randomly moving individuals, right, then what do you think will happen? Then the correlation between their movement will be, what will be the correlation if there are two randomly moving individuals? Correlation between the directions, let us say, very specifically, as Sean said. See, sometimes they will be going in same direction. The correlation in such a scenario will be how much? Maximum, right? Close to plus 1. When they are going in opposite direction, what will be the correlation?
-1.
-1, right?
Oh,
And if they are randomly moving,
0.
+1 and -1 will happen probably equally likely. Likewise, +0.8 and -0.2 will happen equally likely, right? So likewise, any two, so all such pairs of positive or negative correlations will happen equally likely, right? So therefore, the average will be equal to 0. On the other hand, if individuals were to copy each other's behavior, right, then what do you think will happen in such a case? In such a case, what you expect is that the correlation will be high. Okay, so one can exploit this property to find whether how is the interaction between individuals in group. So this property of correlations was used on a study of pigeons in this paper in 2010. So this was one of the very first studies, not the first study. So one of the very first study, I told you that there were one of the very first mathematical computational model was 1995. Although the really first models were at least 10 years ahead of that, right? And in the following 10 years, there were lots of computational agent-based models of collective movement. The data that actually began to make connections to agent-based models and theory sort of first arrived in 2007 onwards. Okay, so this is one such paper, 2010. So let me just have some quoted sentence I have stolen from this paper. Numerous simulation models have been proposed to obtain insight into basic laws of collective motion. Yet rarely have detailed comparisons been attempted between these models and experimental data. Outstanding questions include whether, for example, all group members are equal, as most models assume. I told you that one of the assumptions of the Vichek model is that all individuals are identical, and that was true in cousin model as well, right? as most models assume for the sake of simplicity, or whether one or small number of leaders are able to contribute with differential influence to the group's movement decisions. Okay, and to address this question, what they did was there was a group of homing pigeons. They GPS tagged these entire flock of pigeons, and what they do basically is they shuttle between two sites. These pigeon flocks shuttle between choose two sites, and when they do, they actually have the entire trajectory at fairly high resolution. I don't remember the exact resolution. I don't know if it's like once in few seconds or maybe even once in, I think it's once in few seconds or even shorter than that. Okay. So you have the XY coordinates, XYZ coordinates of individuals over the entire flights. Okay. So here is an example of 2-minute segments of free flights. There are these 10 individuals, they labeled from A to whatever, A to M. Okay. And you can see that how the trajectory, they're all basically together. You can visually observe that, right? Some tend to drift off a bit, but largely they are all together. So you can't see the Z axis here, by the way. So the 2-dimensional projection of their movement. Okay. So here is how the correlation function works in this case. Okay. So consider two individuals, individual I, which is here, and individual J, which is here, the gray and the darker gray. Okay. So the darker gray is J, and it is moving with velocity Vj. That becomes Vj, another Vj at t plus tau 1, and it is changing. It is moving like this. At every point you have some velocity Vj as a function of time. So likewise, we have Vi, it has some velocity as a function of time. Okay, whereas V flock is the average of the entire flock. Okay, it's about of all the 10 individuals. Okay, so what they are plotting in this panel B is as follows. They're basically plotting the scalar product of these two velocity vectors. Now, when you have, you need to now recall briefly about the scalar product. If we have a scalar product between two vectors A and B, it becomes AB cosine theta. Okay, so if you now plot these velocity vectors, and if you now normalize the cross product, this scalar product by their individual speeds, this quantity can vary between -1 and +1. Okay, so +1 means that they are basically in the exact same direction. Okay, and -1 means that they are going in the opposite direction. Is it clear to everyone? Okay, now here is the interesting thing they plot. They are not multiplying VIT with Vj at t. What they are plotting is Vi at t with Vj at t plus tau. If you remember the correlation function we discussed, autocorrelation function that we discussed for, for example, the OU process, what were we doing there? We took x of t, multiplied it with x of t plus tau, right? And of course, in that case, both the variables were x. That's why it was called autocorrelation function. On the other hand, what you have are two random variables, in this case the velocities of the two different birds. Therefore, this is called cross correlation function. Okay, and what you plot on the y-axis is the time lag between the velocities, and the y-axis, x-axis will be time lag between the two velocities. X-axis, x-axis will be time lag. Y-axis will be this scalar product, or the autocorrelation or the cross correlation function. So now let me try to explain this a bit more. How do we deduce leader-followership relationship from this cross correlation? Okay. So, I think there is a small mistake. It should have been t plus tau. Okay, imagine the following. Okay, if I is the leader, then what happens? What do you expect? Then J will copy the direction of I, right? What this means is that the direction of J would be same as I after some time unit. this should, let's call this T1. Okay, is this clear to everyone? If I is the leader and J is copying the direction of I, J will always, will be trying to copy, but the copying takes some time, right? So let's say T1 is the time it takes to copy. Okay, now if you now look at this cross correlation function at an interval of T1, what do you expect? Vj at T plus T1 will be same as Vi of T, right? So therefore the cross correlation function will be exactly equal to 1. Okay, so that means that basically if this is true, if I is the leader and if J is copying, this Cij, which is a function of T1, will be equal to 1 exactly at T1. Okay, I hope this point is clear. And imagine the exactly opposite is happening, which is the J follows I. In such a case, the sign will be inverted, right? The direction of Vj at a previous time will be the direction of I at the current time step. So therefore, by looking at, let's go back to the previous slide. So looking at where exactly this maximum is occurring. If this maximum is occurring at positive value of lag, that means that J follows I. If this maximum occurs at a negative value, that means that I follows J. Okay, so this is the basic idea. I hope, I know you'll have to really work this out yourself. If it's not clear right now, please do it and convince yourself. So basically, by measuring the sign of lag, we can deduce who is the leader and who is the follower. We can also measure the strength of relationship between the two by looking at the the lag, how much is the lag. Okay, so that's precisely what they're doing here for various pairs. For example, here I is the focal individual. They are now plotting the cross correlation between I, A and M, A and G, A and D, and A and C. What you are seeing is that you will find that M, G, D, C, they all have a positive lag. At a positive value, they are reaching a maximum value. That basically means that M, G, D, C, they're all trying to copy the direction of A. Now let's look at, on the other hand, D. D is interesting because one individual has a positive lag, 3 individuals have a negative lag. How do you interpret this? So this triangle would be C. How do you interpret the relation between D and C? C is following D. Okay. How do you interpret these 3 relationships? Let's say A. Does A follow D or does D follow A? Not clear? So if there's a negative lag at which the maximum occurs, right, then the focal individual follows the other individual, right? So it means D is following A. Okay, and that is consistent with what we have found in the top row. Okay, and look at C. What is, because all the lags are negative, that means that C is following all of the 4. Okay, so that's the way to interpret this. And also look at the strength of the correlation on the y-axis. Of course, in the mathematical idealization, I showed that you reach a maximum of 1, but that doesn't always happen. Okay, maximum of 1 means you are really following that strongly, but a weaker correlation maximum means that you are following that somewhat weakly. Okay, so by using this combination of lag and the strength of the auto cross correlation, what they did in this paper was constructed a hierarchy of who is following who. So as you can see that M follows A, and M is followed by G, right? Also followed by J with a strength 0.8, also followed by I with a strength 0.6, and so on. So they basically, what they found was about 2/3 of the pairwise comparisons between birds of a flock produced clearly directed edges. Okay, there was a very clear directionality, meaning that they were consistently, one was following the other. Okay, which also means that in terms of the directionalities, those birds, birds tend to occupy consistently the directional behavior of the particular individuals while being copied in their orientation and choice by others. Okay, so imagine if there was no directionality to the entire graph. Right? If I measure for some amount of time, I found that A follows M, or M follows A. Imagine I measured this after a little while. If in that case, A was following M, that means that what you had found was purely by some positional accident. That means A will follow M for some time, M will follow A for some time. That basically means that they're just copying each other. There's really no leader among them. But the fact that there is consistency in about 2/3 of their pairwise comparisons mean that they're more likely to follow some specific individuals over the course of their entire trajectory. Okay, so let me just read more from the paper. Do, for example, leader-followerships within specific pairwise comparisons extend across multiple flights? They in fact find that this is not true for a single flight. Across multiple flights, some birds are always consistently above the hierarchy, meaning they're probably leaders. Okay, and they also find that there is a spatial correlation. Individuals occupying positions near the front of the flock also tend to assume leadership roles. Of course, this leadership role is very anthropomorphic phrasing. Just keep that in mind. And then they say that our data also indicate that when birds perceive a particular partner predominantly to the left eye, they respond more quickly or strongly to its movement, suggesting that social information might be preferably processed through left eye, right hemispheric system. So this is a interesting biological aspect. I think some of you in the biology background would know that different organisms have different dominant parts of the brain, and depending on that they may have preference of how they process information from different eyes, and that seems to be true with these birds, that they seem to use left eye predominantly. They follow individuals on the left side better in general. Okay, now any questions before I go forward? Any questions? Okay, so I'll move forward. Okay, so let's ask a more general question now. Okay, this is what they found in the context of pigeons. What about other birds? What about schools of fish? Will there be such hierarchical relationships? And also one can ask, what is the nature of interactions? How do they relate back to the simple agent-based models of which et al. Or cousin et al. That we discussed in the beginning. Okay, so let's discuss more about these issues. I'll do this with the example of another paper again in 2010 on starling flocks. Okay, so what you are seeing here is the constructed velocity vectors of these starling flocks. Okay, now these starling flocks are numerous. Sometimes in these flocks there are thousands of individuals. Okay, so you cannot really rely on trying to or hoping to tag all the thousands of birds, right? And there's another interesting feature that happens in many of these birds. Unlike the homing pigeons, which seem to stay in a pretty cohesive group. Okay, if I'm right, even their homing pigeons were probably not from the wild, but they were probably from a certain you know, they were not from the wild. They were probably in some artificial condition. I don't remember exactly what exactly it was. Okay, but but unlike those here, even if I were to pick 1,000 starling birds, if I were to put some GPS stats, which is actually very hard by the way, and if I were to then put them, go them away, if I now observe a flock of starlings, will all of them have tags? All of them have GPS tags? No, because the starling flocks exhibit something called fusion dynamics. They don't stay in the same group. They constantly sort of merge and split among various groups, and there is really basically no hope that by picking even if I pick 1,000 individuals and leave them, they will flock together again. Okay. So what they did in this case was they actually used a 3D camera setup mounted on the top of the top of the building. In this case, the physics department in Rome, and then they tried to they basically took images, and because they used multiple cameras, they were able to construct 3D positions of the flocks. Okay, and this is what they do. So here is what you are seeing is the total, the entire flock, the actual velocity vectors. What you are seeing here are the velocity fluctuations. So basically compute the global velocity, average velocity of the entire flock, and then what you do is for each bird subtract its velocity with that of the entire average velocity. Here all the you do it both ways, one by normalizing by the mean, which is the speed, normalizing by the speed, and the other keeping the speed. And what you are seeing here is basically that there is a lot of fluctuations in the local order. That is not necessarily very evident if you just look at this entire flock. Okay, and what they now do is, now in the previous study, what did they do? They calculated correlations in the velocity vector in time. They were calculating the autocorrelation in time. Sorry, the cross correlation between the birds' velocities, but separated by time. What they compute here is that they compute the cross correlation between the velocity vectors of two individuals, but separated by distance. This is called spatial spatial correlation function, whereas that was temporal correlation function. Okay, so here the lag will be in distance, whereas the lag there will be in time, which is why I chose these two papers to sort of contrast correlations in time in the previous study and correlations in space in this study. And of course, what they do is they don't calculate the correlations in the absolute velocities, but what they do is they calculate correlation in the velocity fluctuations. So for example, here there is some fluctuation, here there is some fluctuation. How are they correlated? If the fluctuations are very similar, then this CR will be close to 1. If the fluctuations are very far away, were very different, then this CR will be close to 0. If you take very nearby regions of the flock, what do you think CR will be? For example, look at this. If I take very nearby areas in the flock, what's the fluctuation correlation going to be? Minimum or maximum? You can just see and guess, right? So these are very nearby, right? These are all fluctuations that are plotted. Are the fluctuations here and here very similar, or are they very different? Close by areas. Again, two close by areas. Again, two close by areas. What do you think?
They should be similar.
They are similar. No, that means the CR will be close to 1 if you are considering a very small spatial lag. What if you consider a large spatial lag? This is, let's say, correlation between this part and this part. The correlation will be very small, right? Because they are now very far away. So you expect basically CR to decay with distance. Do all of you agree with that? So you expect this correlation to decay with distance. Okay. Now imagine the following. Think about the following issue. Imagine I take a flock size of 50. Let's say that the C of R has declined at some distance, which is 5 meters. Okay. If I take a flock size of 100, not 100, what do you think? Where do you think? How far do you think the decay will persist? How far do you think the correlations will continue? Will they continue for longer distances in a larger flock? Okay, so I understand this might be a difficult question to ask. Not so. What I am basically asking is the following: imagine you have taken this flock and taken very large flock. Okay, and if I look at the relationship between two distances, do you think the flock size should matter? By the way, what do you think this fluctuation even measuring? Why are we even measuring fluctuation properties here, by the way? What does it mean to say that the fluctuations here and here are similar, but here and here are not very similar? What does that tell us?
When you say flock size, are you also considering the density?
No, the density remains same in all usually. Let's think of number of individuals.
Okay.
So let's think of why are we talking about fluctuations? Let me give you a context. Let us say there is a predator that attacks this. Okay, there will be some fluctuation that happens at this edges, right? Because these birds saw there was a predator. Is that right? Now for the entire flock to now respond, what should happen to the fluctuations that was caused by the predator? Fluctuations must
to the other parts of the flock.
exactly. The fluctuations must propagate through the flock, right? Okay. Now, do you think this C of R is measuring something on those lines? So imagine that if we take again, let's take a two nearby regions, right? If the two nearby regions have similar fluctuations, that means that the information content is very similar between these two regions, right? On the other hand, if the fluctuation here and the fluctuation here are basically independent, then that means the information hasn't reached that distance, right? Is that correct? Okay, so that basically means that if I take two regions, if I keep on increasing distance, there will be some point where the fluctuations are going to be different as a function of this. Basically, there will be a point of time the fluctuations will become independent, right? When that means CR becomes 0 at that point. Okay, at that distance, you can say that the flock, the information hasn't propagated beyond that distance. Is it reasonable to say? So basically what I'm trying to argue is that this function can measure how much how long the distance can, how much distance the information can propagate about fluctuations. Okay, is that concept clear to everyone? I don't hear any response. So please think about this. This may not be a very easy point. Okay, it requires something through it. Maybe for now you have to accept my word. Okay. Okay. So now let us say, going back to the context of predation, right? If the flock has to somehow respond well, this information must propagate as strongly as possible, right? Now, so what they basically did was they computed the distance to which these fluctuations are propagating for different flock sizes. That's what they do in this paper. Basically, this is how it looks like. This is the correlation function. This is the distance. So they compute this correlation function. They find that it hits 0 at some point. Let's call that, it's called the distance xi. Okay, and they compute the similar parameter when they calculate the correlation function for speeds and when they calculate this for orientation. They compute two different psi values, one for the orientation, one for the speed. Okay, they thought both of them is important because when a predator attacks, not only the orientation of the birds change in response, but the speeds will also change. So you want to know how much the information about change in speed and change in orientation is propagating. For example, what you are seeing here is for a one single flock, one can say that the correlation persists up to around 12 meters in the orientation, around again 12 meters in speed. Is this clear to everyone? This is for one flock that they have measured. Okay.
Is there any assumption of the rate of propagation?
So here they are not measuring anything about time. Okay. So they're using a single snapshot. Okay. So you can sort of think of it as a loosely, very, very loosely as what ecologists will call space for time substitution.
Okay.
Okay. Yeah. But it, it's, it works well if you do lots of realizations and so on here. Okay. So they measured this psi for a number of groups, small groups, big groups, very, very big groups. Okay. Let us say this was, let me ask you the following question. We have measured psi. Okay. Let's say this was for a flock size of, let us say, 1,000. Okay. Let's say if you now measure psi for a flock size of 100, what do you think the psi will be? Will it be small? Will it be larger? Will it be same? If this was 1,000 for 1,000, if it was 100, flock size 100, what do you think this will be? You can make a guess.
I think it'll stay the same.
Okay. And what if it was 10,000? 100 will remain same. This was 1,000. What if it was 10,000? The distance to which this information has propagated. That's the interpretation of psi. Okay.
I mean, I think it would make more sense for the group size to be a function of like this decay function, right? Like
That's a very functional point of view, right? You're thinking of the group function, the function, you think of the adaptation of a group point of view. Don't do that. Pure think from a more mechanistic point of view. Okay, so this psi, could remain same as a function of group size, flock size. That's one possibility, right? Okay, if that is true, that's what I think Abhipsha said, right? So if that, what does that mean? It basically mean what's the implication of this? Distance the information travels is constant for all flocks, right? That means if that is indeed the case, let's go back to the adaptation that point that Sean was talking about. In that case, is it reasonable to say that smaller flocks are better in terms of transferring information across the entire flock? Is that right?
Yes.
Okay. This is what. Is there any other possibility than this?
something like signal boosting, like
let us assume individual behaviors do not change as a function of flock size. Okay. Any other possibility? Oops. Okay. Let me provide another possibility. For very, very small group sizes, the flock size itself could be smaller than, okay, uh, uh, the maximum distance that the information can travel. Okay. So basically, imagine if the flock size was 5, okay, then the information will travel to everyone because it's just such a small flock size anyway. If it was 10, again it will travel to everyone. Okay. If it was 100, maybe they reach a saturation. Okay. So one possibility is that this psi can increase with group size, but it saturates after some threshold flock size. Is that reasonable?
Yes.
It is sort of still consistent with what you said. Just try to make it slightly more nuanced. Oh, I don't know why this happened again. I should now go back to could increase of what I wrote? I also don't know. Okay. Okay, that's another possibility. Let us see what they actually find. This is what they find. So what they find is that this length as a function of flock size kept on increasing for all the flock sizes they measured. Okay, this goes from the flock size of 10 to 80, but I just want to emphasize one thing here. The flocks are three-dimensional. The flock size they are measuring by some measure of volume of the entire flock, which means that you're really looking at the flock size technically is the cube of the values on the x-axis. Okay, an 80 flock size will have, compare say 10 versus 80, right? The 80 flock size, if it was a linear flock, will have 8 number of birds as the 10 flock size, okay, 10 meter flock size. But because it's a cubic flock, it's a three-dimensional flock, the number of birds in this flock size will be 8 cube times that of in the flock size of 10 meters. Okay, that's the way to think about this. Keeping that in mind, what you see is a huge range on the y-axis. Okay, and what you find basically is that this correlation length basically is continuing to increase. It's neither constant as Abhipsha predicted, and it's neither sort of it's neither saturating as I sort of just made a modification. It keeps on increasing. So based on, and this the same pattern holds true even for the flock for the speed correlation length. They find the same pattern, and from this what they actually infer is the following: the correlations do not depend on the scale of the flock. As the flock size increases, the correlation length is increasing. This is a sign of the fact that there's really no scale to the system. So this is the main argument in this paper. It's called scale-free correlations. So basically their argument is that if we had a next bigger flock, this would be even bigger, it would be bigger, and so on and so forth. Meaning there is really no limit technically. Although there is a limit within each flock, technically there is no limit. Just by increasing flock size, you are not going to reach any sort of limit in terms of in terms of how much the information can actually transfer within each flock. Okay, and so that's called a scale-free behavior, meaning there is really no scale to the system. It's similar to the idea of lack of scale in Levy flights that we studied in the very beginning, right? So when we had a Levy flight where that exponent of the Levy flight was between 1 and 2, there was no mean value, and there was no mean value of the entire distribution. There was no variance of the entire distribution. It meant that it could be as high as you could wish. Okay, so that's precisely what something like that might be happening in this stalling flocks, is what these people actually said. Let me tell you one thing very interesting. This guy, Giorgio Parisi, was one of the Nobel laureates this year in physics. Okay, so Yeah, so that was the interesting point. This is an example of also again an emergent pattern, right? So this is the scale-free pattern cannot be attributed to any individual behavior per se, right? Individuals are still following their nearest neighbors most likely, okay, or at least some number of nearest neighbors. But what you are seeing at the level of groups is a property that can only be defined and thought of at the level of groups. They don't even make sense at the level of individuals. Okay, so any questions on this interpretation that I just mentioned? Okay, so let me I have few more slides. I think I'm done. Okay, I'll just stop here. I think I'm done. So we will also 5:30 now.